presentation of the health aspects of the issues that we're dealing with today. Before our break for afternoon tea, the third speaker is Emmanuelidis. I'd like to thank him especially because he stood in at the very last minute when the speaker who we had invited was unable to come. Philibor is a high-energy particle physicist by training. He worked in Stanford and in London and in Paris Sud, and he has since been in the financial sector. He's an actuary, and he's going to tell us about the financial implications of extreme weather.
Thank you very much. Good afternoon. First of all, I would like to thank the organizing committee for having me here. As a scientist, obviously, I understand the honor of talking to the Isaac Newton Institute, so thank you very much for that. Before I start, I should probably find my presentation. There we go. Up. So as we said, I'm going to discuss about a sort of slightly, probably less inspiring side of the mathematics of planet Earth, the financial side of being able to understand how the planet works so that we can protect and prepare for it. Before I start, I would like to also make a small parenthesis. I share a common past with Lord Hunt, having spent a good part of the last decade at UCL. And I remember in my undergraduate degree, I studied physics, but I did a course called Physics of the Earth, given by Seymour Luxon. And I remember being confused by all the strangeness of physics as an undergraduate, quantum mechanics and what have you, how I was fascinated by the simplicity and yet complexity of the mathematics and the physics of planet Earth. After that, I went to do particle physics, which was complex in itself. And as luck has it, I ended up working actually again with mathematics, trying to understand and describe how the planet works. So, a brief summary of what I'm going to talk about. I'm going to talk to you about how mathematical modeling of the planet and of extreme climatic events affects the financial sector, and in particular the insurance industry, which is where I work in. So I'm going to give you a brief introduction on insurance in general as a concept, and then how we view risk and how we distribute it via, for example, reinsurance. Obviously, a big part of what reinsurance does is protect against natural catastrophes, i.e. extreme climatic events. So we're going to briefly talk about that. And then I'm going to talk to you about a few of the more sort of particular aspects of catastrophic events, how they are viewed and shared, the risk they produce in the capital markets, how risk management for insurance companies tries to incorporate mathematical models to protect and to brace against such events. Finally, a bit of a brief tour of catastrophe models, which is essentially what most of you guys would be working on. And finally, one slide on the latest extreme climatic event we experienced, which is Hurricane Sandy, which was only a month or so old. Okay, so insurance is a necessity of everyday life, I'm afraid, and it's been so for the last few centuries. And it's based on the fundamental principle of pooling resources together so that we can protect or we can prepare ourselves for an extreme event. So essentially it's the law of large numbers. So we all pool together our resource, and that resource can be utilized when needed for example, paying claims in the case of an extreme catastrophic or otherwise event. Obviously, this sounds simple, and it's not as simple as it sounds in reality. Also, I should mention that insurance is one of the most of the financial products that have the deepest penetration in our society, for the mere fact that our life is insured, our health is insured, we all have pension plans, our houses are insured, our cars are insured. This building is definitely insured. Even this event could be insured. Many things in our everyday lives could be insured, and hence this provides obviously a lot of fees that we all pay to get insured, which creates a lot of capital that the insurance industry manages. Insurance typically is split into two sections, what the industry calls as life and non-life insurance, and the industry has this sort of simplistic view of calling something and then the opposite for the other thing. So you have life insurance and non-life insurance, as you have what is called marine insurance, which covers marine boats, and then everything else they call non-marine, i.e. property. So it's one of those things that you have to live with. Okay, so today we're going to focus on non-life, i.e. property and casualty insurance, which is where, for what I do, catastrophic events have an importance. Obviously, also needless to say that mathematics have always been important to insurance, because it's quite important to be able to calculate what each member of this pool should contribute to the pool, so that the pool, when it needs to pay for a catastrophic event, it has the correct resource to pay for that. I.e., what is the premiums we should all pay, so that when we need to claim from our insurance company, the money is there. So that was always an important question. This quest of pricing risk essentially started, hundreds of years ago as basic rules of thumb and simple statistical arguments, and has now evolved into a very broad subject, which is called actuarial science. And for the last 20 or so years, the industry has embraced something that is called catastrophe modeling, which is the particular proper physics science taken into account to try to account for natural catastrophes and to provide information to the industry so that it can quantify that risk correctly. But let's start from the beginning, just to give a few, basic numbers to the industry. So, the London market, the UK is one of the fundamental, the largest hubs of insurance in the world. There are 300,000 people employed in insurance and reinsurance in the United Kingdom, and in London alone is 50,000. And the gross premiums for this industry are estimated to something like £37 billion in 2010. So it's a very big sector of the UK economy. It has all of the world's largest insurers and reinsurers, as well as Lloyd's of London, which is a very unique corporation in its own, and other key facts about London as a sort of global hub of insurance. So this is the London market. Now, a little bit about insurance concepts. So typically insurance companies, as we know them, are localized entities that are taking on risk from individuals or corporations in that local area, i.e. Cambridge Insurance Company is probably going to insure houses in Cambridge, which means it has very localized risk. If something happens in Cambridge, that company will have a big problem paying off the claims. For that reason, to diversify, it uses a process called reinsurance, where a localized company in a line of business or geography, right, insurers A to D that we have there, will cede or pass on some of the biggest risks they have to what we call reinsurance companies. Reinsurance companies are just insurers for insurance companies. So essentially they are one step up in the diversification chain, more global companies that will take a bit of risk from insurance company of Cambridge, a bit of risk of insurance company of Oxford, a bit of risk for insurance company of Athens, which is my hometown in Greece, and then hopefully by pulling in all those risks together, once a catastrophic event takes place in one of the three locations, not all of the risk held by this reinsurance company will request a claim, essentially, so the company will be able to remain solvent. And this is the concept of diversifying and seeding in risk globally so that companies can handle their local business and still be in business. So there are obviously more insurance companies than reinsurance companies, and reinsurance companies, as we said, tend to be more global in that they need to diversify by territory as well as by peril. And then you have this strange place here, and as it happens in this sort of diagrams, you get spirals of things going on top of each other. So this is called retrocession, which is reinsurance for reinsurers. And this serves the purpose to diversify the peak risks that reinsurance companies cannot diversify themselves. And I'm going to explain what I mean in a few slides. But essentially, when the insurance and reinsurance capacity has maximized its diversification potential and starts having concentration of risk, these guys are needed to take some of that risk and diversify further. And these tend to be capital market participants. One of the instruments or asset classes in this is called insurance-linked securities, which is what my company and I do. I'll come on to that later on. So this is the basic principle of distributing risk in the insurance industry. A bit about natural catastrophes. We heard before what has happened to the world over the last few years. 2011 was a slightly unique year in the sense that too many big events took place in the same year, which created record economic as well as insurable losses to our industry. For example, you had the New Zealand quakes, you had the floods in Thailand, you had the big earthquake and then ensuing tsunami in Japan, you had a hurricane in the US, there are many tornadoes and severe convective storms as well in the US, producing a lot of insurable catastrophic losses, not to mention obviously all the economic losses that took place, and of course losses of life that took place in places like Pakistan and Turkey. So a very significant year in terms of catastrophes, which shows how much of this risk is around and we face. Just putting a few numbers on the previous slide. So unfortunately, as I said, it's a financial presentation, so I'm going to be talking on insured losses rather than economic, even though I feel I should be doing the other, the economic view. But for example, the Japan quake is estimated to have produced about $35 billion of insurable loss. The economic loss to this is multiples higher because of the insurance take-up rates in Japan. And then the two New Zealand quakes produced a lot. The floods in Thailand produced quite a lot of loss. This was mainly due to business interruptions because of a lot of factories were flooded in these areas in Thailand. All in all, this year contributed to just over $100 billion of insured loss. So very big numbers. Now, comparing these to the numbers of the insurance industry, they're a bit smaller. The non-life, as we said, the property and casualty insurance premiums are a very big number that I dare not say. The non-life reinsurance premium as part of this is about 150 billion, yet a big number. And this is the catastrophe premiums attributed in the reinsurance industry to catastrophe risk, which is about $10.5 billion. Now, the interesting thing to notice is that here you have a spread of countries for these premiums. And okay, there is a fair spread between, for example, Europe, the US, Asia, etc. When you go to reinsurance, that spread sort of continues. When you go to catastrophe reinsurance, you see there is a big concentration of US risk, which means that already we can spot there is an accumulation of risk attributed to the US, and this is of course because so many hurricanes, first of all, of course, because so much insurance is in place in the US, and also that so many hurricanes sort of impact the United States. Another slide to demonstrate this is, this essentially shows the residential population change, increase, in different states of the United States from 1960 till 2010. And you can see that Florida has almost tripled, and obviously Florida is a very catastrophe-prone state, being in the path of many hurricanes. So this shows that insurance concentration is increasing, and this risk is a risk that is very hard for reinsurers to diversify, and hence, as I mentioned a couple of slides ago, the need for diversification through capital market participants, i.e. spread the risk outside of the reinsurance industry. Okay, so we talked about the industry and how it behaves in general and the need of diversification. Where do mathematics come in? So, risk is the general theme of insurance, and these are the various risks that an insurance company would face. So, an insurance company would need to hold assets to back the liabilities, i.e. when you pay a premium, the insurance company puts that premium in the bank or buys a bond, and that bond hopefully will pay you back, or will be there to pay you back if you made a claim. So the insurance company will have a risk from the assets losing value, will have operating risks, as most companies do, and then we'll have what is the most important, liability risks, i.e. how much did it charge the correct premiums for the risks it took on, and will it be able to pay off the claims if such arise. And these are split for a traditional non-life insurance company into catastrophe and non-catastrophe risk. And we're going to talk about catastrophe, of course, because that is what captures the extreme climatic, or as we call them in the industry, tail events. So these are losses made due to natural or man-made disasters, floods, windstorms, earthquakes, etc. As was mentioned in the previous, by one of the previous speakers as well, this field really started in response, the field of catastrophe modeling really started in response to big catastrophic events for the industry, as it often happens. So, for example, the European windstorms of 1987 and 1990, Hurricane Andrew in the States in 1992, the World Trade Center obviously drew the attention of terrorism as an extreme tail event, and the 2005 season with Hurricane Katrina among the three in total that took place, big hurricanes. So this has led to the development of what is called catastrophe modeling in the industry, which is the bit of, is not really part of actuarial science, even though there are many synergies, but is the bit that tries to quantify the risk that an insurance company faces as a result of natural or man-made catastrophes. And this part of science for our industry has three main aims: is to help to understand the risk due to natural catastrophes faced by insurance companies, to assist those companies in determining what sort of insurance or reinsurance strategy they should adopt to handle that risk, and most obviously to price those risks adequately so that that company will be solvent and hopefully profitable as it operates and as it pays the claims to the events that arise. Another interesting consideration is that most of these insurance companies, when they're all regulated by a regulatory body, in the UK is the Financial Services Authority, the FSA, and they're typically regulated to some sort of limit of how much capital they should hold to withstand the risks that they take. And a sort of vanilla measure that people tend to mention is that a company should have enough capital to support a 1 in 200 year event, i.e. a year that happens with 0.5% probability, right? But how do you quantify this? This is, we definitely don't have enough good statistics, or we don't know our exposures well enough to be able to quantify this number so that we know how to regulate this company effectively. So it is an interesting subject, especially in insurance when we talk about such distant events. A bit of an anatomy of a catastrophe model, shifting page quickly, is so just to give you an idea of how it all ties together in our industry. You'll see the three main components, which I believe were discussed before as well, is the three main components. You need to have exposure information, i.e., because obviously we're talking about financial impact here. We need to know where the properties and the cars and the what have you are placed and what is their value. So this is an important part. Then this, which is the scientific part of this picture, is the hazard module, i.e. we need to know and we need to be able to model, to project, or at least to understand how the hazard, the risk that we face evolves and what are the associated metrics involved with this hazard. This could be a windstorm, a hurricane, a flood, an earthquake, many other things. And finally, the vulnerability model, which essentially tells you how you apply the effects of the hazard to your exposure, i.e. a certain wind speed and a central pressure and direction of a hurricane track. How would that affect the underlying properties in that tract to produce a financial loss? And obviously this bit is very data intensive, but I wouldn't say it's completely scientific in the sense that it's so complex that it cannot be, so it's vaguely approximate and empirical. This bit is very data intensive, period. There's not much more to it. This is the bit that is of most interest, because this will give you associated probabilities of occurrence. How often do I expect to see an event? Of what magnitude do I expect to see that event, etc. So let's look at it a bit in more detail. An interesting picture, I'm not sure it doesn't show quite well. So, oh yes, you can just about see it. So it's a picture of the world, and all these are hurricane or tropical cyclone tracks for sort of 50, 60 years or so. And you can see how many of them are there. These are all registered by the US National Oceanographic Agency, and these are the different scales that tropical depressions, cyclones, and hurricanes are associated with obviously a Cat 5 hurricane being the worst you can get. So when I was talking about the hazard module, and I'm going to just take as an example windstorms, i.e. this sort of things, what we need to be doing in the insurance industry, rather than weather forecasts and weather predictions, we need to have a good understanding of the hazard that is in place, i.e. what are the associated tracks that could exist in the Atlantic Ocean affecting the US. Due to the dynamics of the climate there, how could these tracks evolve? As we heard, Hurricane Sandy was a weird one this year, because as I was going rightwards, it suddenly turned into New York. So is that allowed? What's the likelihood of that happening? And we need to be able to have a view of this, because obviously this is the risk that our industry possesses when it insures coastal properties in the US, for example. Now, there are two ways for this to be done. Obviously, we can use the deterministic approach, which is essentially we get a lot of historical tracks and we try to pass them through our exposure portfolios, or as it happens lately, there probabilistic models get created that have the physics, the underlying physics engines of how the climate might behave under these circumstances, and start with historical events as a feeder into that physics engine. And by changing different parameters, you end up having a much larger event set, or event catalog as we call it, which essentially gives you a collection of possible events that could take place, and you try to get a view of the risk that those possess to the industry. So essentially, these simulated event sets represent a more complete view of the hazard, including extreme events that may not have been recorded yet. So that is the general, very, very simplified, obviously, approach of how a hazard module would work in the context of insurance catastrophe modeling. I'm not even going to attempt to describe any of this, given some of the people that are in the audience, but but essentially what this says is that we are interested in having a granular view over our models and be able to take sort of the evolution of whatever hazard we try to model, because of obviously the granularity of the exposures that lie under it within this grid, which get affected in our industry, i.e. our insurance exposures. Am I running? I am running out of time. So I'm going to skip this one. A very recent example, as it was discussed previously, is Hurricane Sandy. Actually, it was a post-tropical storm when it hit when it made landfall in the U.S. So it produced about 250 fatalities, but it is considered as one of the costliest hurricanes in the U.S. history. Obviously, because of the location it impacted, New York and New Jersey. The economic losses are estimated to be between 30 and 50 billion dollars, with about 15 to 25 estimated, and these are very rough estimates yet, to be insured losses. So now this was a very unusual storm for the insurance industry, partly because of the evolution, but that is fine, that can be sort of explained, the way it curved inwards towards the US, but mostly because of the amount of damage it caused due to not wind, as hurricanes typically do, but storm surge, i.e. flooding, post-hurricane flooding. So most of the damage, the insurance damage caused by Hurricane Sandy is due to flooding, and I think sort of most people in the insurance industry would admit that we are a bit underweight in our understanding of flooding in our catastrophe models. So I wouldn't be surprised if we see a few interesting stories over the next sort of half a year or a year about evolution of catastrophe models post-Sandy. That said, from the models we use, it was characterized as a 1 in 50 year event, i.e. having a 2% probability of happening. It happened this year. So as I said, the characteristics were not fully captured in existing wind models. That means that the stochastic event sets that we discussed, almost none of those thousands and thousands of probable or possible hurricane tracks reflected actually a track that had this shape as Sandy, with the intensity that Sandy had. So it is going to be, and always has been, a constant learning exercise, in the sense that I'm sure we're all going to go back to study this event, try to capture the characteristics that we learned from this event, and then go and recalibrate and improve our models to be able to capture these events better in the future. And as a final note on the modeling side, I think it's fair to say that the insurance industry, the catastrophe modeling that is used, is dominated by a few professional participants. That is, service companies that most of the industry use, and then they apply their view on a sort of vendor model. As you would expect, Securities, definitely Securities, but most of the big insurers and reinsurers don't have the resource to create these sort of models themselves. I'm sure it takes academics quite a few years to manage to create this sort of complexity of models. So we depend on sort of vendor models, and we take our view on them. And some of them tend to be, black box maybe is a bit too harsh, but there is definitely a bit of uncertainty on what is under the lid. So what I would like to say, and maybe this is the opportunity that should come out of my talk, is that obviously extreme climatic events and catastrophes are a very important part of the insurance industry, as well as hopefully I showed you. And the industry does need more transparency in the way these things are handled. And obviously, probably you gathered a few slides before that the industry has a lot of capital, a lot of money to spend. So maybe a good idea would be a university collaboration that is funded by the industry to create some sort of open source platform for these sort of models to be able to share it and deploy it among the various participants, and obviously share thought and ideas and what have you. The last slide was going to be an introduction to my company, so I'm going to do it as quickly as I can, because I understand you all want coffee, and so do I, actually. So Securities is sits at the top of the pyramid we saw in the first few slides. It invests in very extreme insurance risk. So we take investors' money and we try to price this extreme climatic risk correctly and provide protection through insurance companies through our investments, so that they have they can diversify their concentration of, as we saw, for example, US hurricane risk, which they couldn't diversify themselves. And in the meantime, we hope to get well paid for the risk we get, so that we provide returns to our investors. Thank you.
Well, ladies and gentlemen, that completes the first part of the programme. If we go now and have some tea and resume at, let's say,